All right, this is going to be part one on a little lesson on hydrates. This lesson, we're going to spend just going over basic naming, formulating for basic hydrates. Then we'll deal with the percent composition by mass for the water in a hydrate, looking at it in terms of the formula, and then also in terms of lab data. The next video will then focus on how do we find the empirical formula of a hydrate. So first off, just realize that hydrates are a specific class of ionic compounds in which waters are basically embedded into the structure. So a couple little things here is that this is a fixed ratio. So if we have something like copper 2 sulfate that's a hydrate, it's always going to be pentahydrate with its 5 water molecules that are in that ionic crystal. A couple of things, we're going to be using prefixes to show how many waters are within it. And then also this dot here is not multiplication. It's the symbol that we use to signify that we have a hydrate. So just be aware of that, especially when we get to some of the calculations. So I'm just going to give you two examples of these first two on the worksheet. So you're going to focus on just naming the ionic compound, just like we've been doing with the stock system. Magnesium is a group 2, so we don't need a Roman numeral. So I would start off with magnesium, and then SO4 is your sulfate. Okay, then I'm going to address the fact that there are 7 waters. So the prefix for 7 is hepta. And then to signify again that this is a hydrate, it's going to be heptahydrate. Okay, if we work the other way, which is probably most commonly how you're going to see this, is we have sodium carbonate decahydrates. We need to write the formula. So I'm going to start with my sodium carbonate. Sodium is +1 and carbonate is -2. So we need to make sure we have 2 sodiums, and then CO3. Make sure you include that dot. And then decahydrate is going to be 10 waters. Okay, so this just adds on a little bit to our naming of ionic compounds by just including these water molecules. So the reason why it's important to get the formula is going to be when we're calculating the mass percent of water. And in this first example, we're going to do it based on our formula here. So I'm going to start with writing our CaCl2, that's our calcium chloride, because chlorine is -1, calcium is +2, and then we have decahydrate here. So one little thing, and if you can see in this lesson and the next lesson how this all ties into our earlier lessons in APChem, you'll see that this is just going to be a variation of the part over whole times 100. The part that we're going to be interested in this case is the amount of water we have, and the whole thing is our original hydrate times 100. Okay, so one little thing is, in order to find the water, I'm looking at my 10 waters. I personally like to add up the mass of H2O first and then multiply by 10. I just find if I separate it by hydrogen and oxygen, students will get the 20 hydrogens and then they'll just do 1 oxygen. They'll forget that that 10 applies to the oxygen. So I prefer to do 10 and then I add up the molar mass of water, which is going to be 18.02. Okay, that's going to give me the mass of water there, which is then going to be keeping the 4 sig figs of my GFM there will be 180.2 grams per mole. Okay, so that's going to be up in my numerator over here. The hydrate is going to be the whole thing, including the water. So in that case, I'm doing the CaCl2 plus my 10 waters. So this would be using my molar mass of calcium, which is 40.08, plus my 2 chlorines, 35.45, plus my 10 times 18.02. And when you add that all together, keeping to the hundredths place in this case, 291.18 grams per mole. So now that you've got the molar masses of our water and our hydrate, we can now plug those into this formula. So that's going to be 180.2 divided by 291.18. Make sure you remember to show and write down that times 100. And then in this case, because we're doing a percentage, we are going to just go right to the hundredths because of the percentage. So when you divide those and you times it by 100, you get 61.89%. Okay, and that would be the mass of any sample of calcium chloride decahydrate. 61.89% of it should be due to the water. And we can do various procedures in the lab to verify that. So in number 3, this is a very similar example, except it's giving us information based on a lab scenario. So it's talking about a hydrate, and the student starts off with 4.1 grams of it. They heat it to a constant mass, which is going to be important. to a mass of 3.70 grams. And it wants to know the mass percent of water. So one thing I like for students to think about is you're starting with a hydrate. You're then going to heat it. And what you're left with is called an anhydrous salt. Okay, and this is what's left in the container. So this is the solid left over in container. And then the other part of that when you heat is the water, and this is what evaporated out. So any loss of mass from the hydrate to the anhydrous salt is the mass of the water, which is where the constant mass comes in. If you're heating to a constant mass, you're ensuring that all the water has evaporated out. And we'll be talking about this more when we go ahead with a lab shortly. All right, so let's go ahead then and determine what we need to put where. We're going to have our water over our hydrate times 100. So the hydrate is at starting mass, 4.10. The water is going to be the difference between the starting hydrate and the mass that we were left with after we heated it to a constant mass. So I'm going to write this down as 4.10 minus 3.70 times 100. Okay, you could also simply write that and actually do the subtraction. Just make sure you plug in the 0.40 so that you're showing that you did your subtraction according to sig fig rules. And then at the very end, we're going to get a percentage. And because we're dealing with just a percentage, I'm going to always go to the hundredths place. So that gives me a percentage of 9.76%. So if I had, this sample of a hydrate, 9.76% of that mass is due to the water, which we saw evaporate out of it. All right, so in the next video, we're going to take this one step further and work to determine the formula based on our information.